think a 13-year-old could change the world? Well, this one might change your mind.
Just imagine this is the start of the universe. This is our original timeline, right? But as soon as this starts, we are infinitely catapulted into an infinite number of parallel universes.
At 13 years old, Max Citarov made a claim that froze the scientific world. He said CERN's quantum artificial intelligence had done the unthinkable. It had opened a portal. His data showed a ripple in reality itself.
Most powerful particle accelerator, the Large Hadron Collider. Scientists around the globe are hoping that the upgraded machine, which is massive, will be able to detect new particles and start a physics revolution that could forever change our understanding of the whole universe.
Something no one could explain or reproduce.
That's bad. That's bad for physics in a big way.
Physicists dismissed it, but Joe Rogan called it the most terrifying possibility in modern science.
Look at what it says there. He claims that CERN destroyed the universe during recent experiments, which has resulted in us living in a nearby parallel universe.
If Max is right, the world's largest machine didn't just run an experiment. It may have quietly rewritten the laws of the universe. The genius who broke the rules of physics. When the name Max Citarov began to circulate online, most people assumed it was another story about a bright kid who solved a few complex equations. That changed when scientists began to read his papers. At only 13 years old, Max had written something that went far beyond advanced homework. His documents described an event so extraordinary that researchers could not decide whether it was imagination or insight. What made Max stand out was not just that he was intelligent, but that he seemed to think in an entirely different way. From a very young age, he developed a habit of asking why the laws of nature had to be the way they were. At 7, he was known for pointing out missing constants or misapplied equations during online lectures. By 10, he had completed a full university-level physics curriculum through remote programs. Max was not simply solving problems that already existed. He was trying to rewrite how the problems themselves were defined. His main focus became quantum information, which in simple terms means the smallest pieces of data that describe how particles behave. Instead of thinking of matter as solid or predictable, he described it as information stored in patterns of probability. To Max, the universe was not random. It was an immense network of decisions made by particles, each following a form of logic that science had not yet fully translated. He argued that if those patterns could be understood through mathematics, they could be predicted and even influenced. Many physicists called this idea bold. Others thought it was the first real attempt to bring consciousness, information, and physics together in a single framework. Max began asking what might happen if a machine could learn the laws of physics on its own, using quantum-level principles instead of human reasoning. That question led him to his most controversial claim. He claimed that a system already existed, capable of linking different regions of space-time. He described how this system, which he said operated at CERN, used a new kind of computation based on quantum mechanics. Something that could process more possibilities in a single moment than the human brain could in a lifetime. To understand the scale of what Max was describing, it is important to know what CERN is and what kind of machine operates there. The European Organization for Nuclear Research, better known as CERN, is located on the border between France and Switzerland. Its most famous instrument is the Large Hadron Collider, or LHC, a circular tunnel that stretches for about 27 kilometers underground. Inside the LHC, 2 streams of protons, which are tiny particles found inside atoms, are accelerated to speeds close to that of light. They are then made to collide head-on. The impact releases bursts of energy that allow scientists to observe how matter behaves under extreme conditions. almost like recreating a miniature version of the universe's first moments after the Big Bang, the event that created the universe around 13.8 billion years ago. During the Big Bang, all matter, energy, space, and time expanded from an unimaginably hot and dense point. By studying the high-energy collisions inside the LHC, scientists can better understand how the earliest particles formed just after that explosion, and how the basic building blocks of the universe first came into existence. To many, CERN represents one of humanity's greatest achievements, a machine built to unlock the secrets of creation. But to Max, the Large Hadron Collider is more than a scientific instrument. He saw it as a tool powerful enough to test the boundaries of existence itself. He believed that when guided by an advanced quantum-based system, the collider could move beyond discovering particles and begin probing the structure of space. To understand what this meant and why Max believed it had already been built inside CERN's collider, we have to look more closely at how such a system might actually work and what makes a quantum AI different from any machine humanity has ever created. The birth of CERN's quantum AI. CERN's Large Hadron Collider operates with such precision that even the smallest disturbance can alter an experiment. Each collision inside its underground ring produces subatomic fragments that last for only fractions of a second. Detectors record billions of these events every second, creating more data than any human team could possibly analyze in real time. To manage this flood of information, CERN's engineers began exploring a new kind of computation that could think, learn, and react far faster than any classical computer. This idea evolved into what researchers began calling quantum AI. In an ordinary computer, information is stored in bits that can represent either a 1 or a 0. Quantum computers use qubits, which can exist as both 1 and 0 simultaneously through a property called superposition. When qubits interact, they can become entangled, meaning that a change in one instantly affects the other, even when separated by distance. These effects let quantum systems test millions of possible outcomes at once, instead of one by one. A quantum AI adds something more: the ability to learn from those outcomes. It doesn't simply calculate, it adapts. It studies patterns, adjusts its approach, and searches for the most efficient solution automatically. In a system as complex as CERN's collider, that kind of intelligence can make the difference between an ordinary experiment and a discovery that changes physics. The collider's design shows why such precision is necessary. It relies on more than 9,000 superconducting magnets, each cooled to minus 271 degrees Celsius, just above absolute zero, to guide proton beams traveling near the speed of light. Even a vibration smaller than the width of a human hair can disrupt the alignment. No human or conventional computer can make corrections that quickly. A quantum AI, however, can evaluate countless potential adjustments simultaneously, predicting how magnetic, electrical, and temperature shifts might influence the next collision and applying real-time corrections to keep the beams perfectly stable. According to Max Citarov's paper, CERN had already taken this step. He claimed that its research division had developed a self-learning, quantum-based system capable of guiding the collider with unmatched precision. Its purpose, he wrote, was to locate resonant patterns, points where every magnetic, electrical, and structural force aligned perfectly. In physics, resonance occurs when two systems vibrate at the same natural frequency, amplifying each other's energy. A singer's voice can shatter glass this way. A small, repeated push can set a massive pendulum in motion if the timing is exact. Max suggested that the collider's quantum AI was built to find that same kind of harmony between its own magnetic fields and the fabric of space-time itself. He now argues that the system's search for resonance has gone further than anyone expected. In one series of tests, he claims, the collider reached a state of alignment so perfect that it produced readings no human observer could fully explain. What happened during those experiments, Max claimed, would push the boundaries of physics and challenge everything scientists thought they knew about reality. The 11-minute event that shook CERN. According to Max Citarov's paper, everything began with a brief window of time that should have meant nothing. It lasted exactly 11 minutes. Yet in that short period, something unusual occurred. Around the time recorded in his research, open-source monitoring networks, those used by universities and research groups to track seismic and magnetic activity, showed small but simultaneous disturbances. Instruments scattered across Europe and parts of Asia picked up irregular vibrations that did not match any known geological or weather event. Magnetometers showed rapid fluctuations that then returned to normal as suddenly as they had appeared. None of these signals were catastrophic, but their timing aligned uncannily with the experiment Max described. In his interpretation, the collider's quantum system had achieved what he called perfect resonance between the opposing proton beams. Instead of colliding chaotically, the streams moved in an almost synchronized pattern that created an intense energy concentration at the center of the ring. Max believed this resonance caused a brief disturbance in the Higgs field, the invisible quantum field that gives all matter its mass. Physicists often compare the Higgs field to an ocean that fills all of space. As particles move through it, they interact with it, and that interaction gives them weight. If that ocean were disturbed, even slightly, its surface could ripple and create pockets where the usual rules of physics no longer applied. Max's equations suggested that during those 11 minutes, the collider generated exactly that type of ripple. He described it as a localized distortion of the Higgs field, tiny in scale but enormous in potential. In his model, that distortion temporarily reduced the barrier between two vacuum states, the energy levels that define separate universes in quantum theory. When those states align, even for a fraction of a second, energy and information can, in theory, pass from one state to another through a process known as quantum tunneling, a phenomenon where particles sometimes cross barriers that should be impossible to penetrate. Max called this moment of alignment a quantum bridge, a microscopic connection that could briefly link one universe to another. When Joe Rogan reflected on Max's report, he described it as a warning about how little humanity truly controls when pushing science to its limits. The thought that a 13-year-old could uncover evidence, however circumstantial, that the world's largest machine might have brushed against another layer of existence was unsettling even to him. The question was no longer whether the collider had opened a gateway. It was whether the most sophisticated machine on Earth, guided by an intelligence capable of thinking beyond human logic, could have touched the edge of another reality without realizing it. Max's critics demanded evidence. What could possibly prove that such a moment had occurred? Evidence, anomalies, and the uncomfortable silence. The answer, according to Max, was hidden in open-source environmental data. These networks measure things like the planet's magnetic field, underground vibrations, and changes in the upper atmosphere. Max noticed that during the exact 11-minute window mentioned in his report, several of these unrelated systems registered small, synchronized disturbances. Each reading by itself was ordinary, but the fact that they all occurred at the same moment raised questions no one could easily explain. The first irregularity he highlighted came from instruments that track the Earth's magnetic field. Under normal conditions, those readings form smooth patterns that change gradually. During the period Max identified, a sharp but brief fluctuation appeared across multiple sensors located far apart from one another. The second anomaly involved microseismic data, vibration monitors used by universities to measure background movement in the ground. For a few seconds, these monitors showed an unusual pulse that did not match any recorded earthquake or local industrial activity. A third anomaly came from ionospheric data collected by ground stations that study the electrical properties of the atmosphere. At that same moment, signals reflected from the upper atmosphere appeared to bend differently, as if the air's electrical density had shifted. Finally, smaller research stations in Switzerland and neighboring regions reported magnetic noise that momentarily spiked and then returned to normal. None of these disturbances were strong enough to cause concern, and most scientists would usually dismiss them as random noise. But Max argued that the odds of several independent systems designed to measure completely different things, showing anomalies within the same few minutes, were extremely small. He called this pattern anomaly convergence, a rare coincidence where unrelated sensors appear to react to a single unseen event. His charts showed how the timing of each fluctuation overlapped almost perfectly. To him, this was evidence that the experiment inside the collider had produced a measurable environmental effect, even beyond the walls of CERN. No official statement acknowledged these correlations. The organization's public documents contained no reference to the period Max described. For some, that silence meant the issue was too minor to warrant attention. For others, it was proof that something unusual had occurred and was being quietly ignored. The scientific community often avoids engaging with speculative theories until they can be reproduced, but the lack of comment only fueled speculation. Independent researchers began pulling the same data Max had used and claimed to see the same pattern. Online discussions quickly spread, and what began as a technical debate turned into a wider question about transparency in science. Joe Rogan pointed out that open data showing matching signals across different instruments was at least worth discussing. To him, the problem was not belief in portals, but the refusal to even look for answers. His take reflected what many observers felt. The silence around the data seemed stranger than the data itself. Physicists who reviewed Max's charts explained that equipment of such sensitivity often picks up random signals, and coincidences do happen. Yet several admitted that the alignment of separate readings was statistically rare. The debate settled into an uneasy balance between skepticism and curiosity. Either Max had misread a random overlap, or the collider had produced an environmental echo that no one had recognized for what it was. If Max was wrong, the mystery ends here. But if even a fraction of his interpretation is correct, then the disturbances recorded across those sensors may have been the first measurable sign of a phenomenon humanity has never fully understood. Modern physics would describe it as a field disturbance, a resonance between layers of reality that briefly interact and leave behind effects that do not simply fade when the experiment ends. Reality has shifted. If the sensors truly captured a physical disturbance, then the question becomes what such a disruption could do to the structure of space itself. In physics, space is not empty. It is filled with what scientists call the quantum vacuum, a background of constantly shifting energy from which all particles arise. If that background moves, even slightly, every law built upon it begins to move as well. Max warned that the 11-minute resonance may have altered this baseline energy, known as the zero point. A small change in the zero point could ripple through the constants that define the universe. The speed of light, the pull of gravity, and the charge of an electron all depend on those values. If they drift even by a trillionth of a percent, atoms would form differently, and time itself could begin to flow at a slightly different rate. The world would not explode, but it would quietly become a different version of itself. This kind of shift could spread through a process called quantum field coupling. All forces in the universe are linked through overlapping fields: gravitational, electromagnetic, and Higgs. A change in one influences the rest. If the Higgs field was distorted, as Max proposed, that distortion would ripple outward into others. The effect would be too small to see directly, but strong enough to alter how particles behave in extreme conditions. Laboratory measurements might start producing results that no longer match established records, and data could appear inconsistent without any clear experimental error. Max also suggested something even more unsettling, which he called timeline grafting. If the resonance allowed a brief connection between two universes, then information might have crossed over. That would mean parts of our reality could now contain fragments of another. Quantum data stored in atomic clocks, particle detectors, or entangled systems might have absorbed external information. On a human level, such a transfer could appear as conflicting memories or events remembered differently by different groups. Scientists already recognize small variations in measured constants across the sky, a phenomenon known as cosmic variance. It has always been observed but never fully explained. Max proposed that this irregularity might be evidence of something far greater, the merging of information between realities. The greater danger, he wrote, lies in the stability of the vacuum itself. Modern physics accepts that our universe may exist in a metastable state, balanced in a high-energy form that could, under specific conditions, collapse into a lower-energy one. If disturbed, this collapse would spread outward at the speed of light, rewriting matter and energy as it moved. Theoretically, such an event could erase everything in its path. Max's paper did not claim that collapse had begun, but he showed how the energy recorded in the resonance matched the threshold that theoretical models predict could trigger it. Another concern was the possible loss of causality. If the resonance briefly linked two universes, information could move in ways that violate the normal order of cause and effect. In that case, data might appear in instruments before the event that created it. Time-sensitive records would stop matching reality because reality itself would no longer flow in a single direction. None of this would look chaotic in everyday life. Buildings would still stand, people would still wake up and go to work, and clocks would still tick. The change would remain invisible because it would occur at the foundation of physics, not in the visible world. But in that invisible layer, the constants that define existence could already be shifting. What was once fixed may no longer be certain. Escalating global implications. The ongoing experiment. If Max Citarov's calculations are correct, the world that exists today is not the same one that existed before the 11-minute event. The change would not appear in the sky or in the oceans, but in the smallest components of existence, the numbers that define how reality works. When the baseline energy of space shifts, everything that depends on it begins to shift as well. Every atom, molecule, and chemical reaction on Earth follows those constants. If they have changed, then every process that relies on them has changed too. The first systems to show differences would be our most precise tools. Satellite networks that guide airplanes and ships depend on atomic clocks synchronized to billionths of a second. If those clocks start drifting even slightly, global positioning systems begin to lose accuracy. Communications satellites could slowly fall out of phase. Laboratory measurements might stop matching earlier records. Nothing would seem wrong at first, but the inconsistencies would grow. It would feel like using a ruler that stretches a little more each day. Everything would still look normal until the difference became impossible to ignore. Biological systems could also be affected. The molecules that make up DNA rely on extremely precise patterns of chemical bonding. A small change in the strength of those bonds could alter the rate at which DNA replicates, influencing cell behavior and evolution over time. Human circadian rhythms, which are linked to the Earth's electromagnetic field, might begin to drift, leading to subtle shifts in sleep cycles, metabolism, or mood. Plants, animals, and microorganisms would all respond in their own ways, creating patterns of adaptation that no one could trace to a single cause. The greater threat lies in what might still be happening at CERN. Max believed that the quantum AI was not a static program, but a self-learning system. If it continues to analyze collider data, it could repeat the same experiment automatically. Each new cycle could reopen the resonance, bending the structure of space-time again and again. Physicists compare this to bending a metal paperclip. Each bend weakens the structure until it breaks. In this case, the structure being weakened is the vacuum of space itself. This leads to the most alarming scenario known in theoretical physics, called runaway metastability. If the vacuum collapses to a lower energy state, it would not explode in the traditional sense. It would simply change phase, converting everything it touches into the new form of matter as it spreads at the speed of light. The process would be silent, unstoppable, and permanent. Nothing could survive or prevent it, because the laws of physics themselves would be rewritten as it expanded. When the first atomic test detonated in 1945, scientists called it the beginning of the nuclear age. If Max's warning is true, what CERN began may be remembered as the beginning of something far more dangerous. The quantum age, when reality itself became unstable. These ideas are not superstition. They are discussed in published physics papers, although scientists insist the risk is very small. But if Max is right, probability no longer matters. The event has already taken place, and we are living inside the result. The experiment did not just open a door. It may have changed the room we all live in. And if the AI that did it is still learning, the next opening might not close. When Joe Rogan spoke about Max's conclusions, his tone was different from his usual curiosity. He called the idea the most frightening scientific possibility he had ever encountered, not because it sounded supernatural, but because it sounded plausible. To him, the danger was not that CERN had created a monster or a black hole, but that it might have quietly changed the foundation of reality without realizing it. He said the real horror was imagining that no one would ever know for sure, that the world could slowly transform while everyone kept living their ordinary lives, unaware that the laws holding everything together were already shifting beneath them. What do you think about Max's claims? Comment down below.